Hey guys, and welcome to another video discussing this idea of modeling real-world situations with linear equations and linear graphs. So let's talk about your energy bill. So of course, every month your energy bill depends on how much energy you use. By the way, I'm making this lesson in the dead of winter, and it is so cold outside, and my energy bill was so much last month. Okay, anyway, all right, venting session over. Here we go. The unit that's used to measure how much energy you use is called the kilowatt hour, kWh for short, which you may learn about in physics soon, or maybe you already learned about it in physics. Anyway, 1 month you used 315 kilowatt hours of energy, and the total cost was $90. And another month you used more energy, you used 360 kilowatt hours, and the cost was $99. And we're making a big assumption that each kilowatt hour costs the same amount. It's not like the first kilowatt hour you use cost this much and the next one costs another amount. It's the same amount per kilowatt hour. So all we really need to do is we need to find that rate of change. If we can find how much each kilowatt hour costs, we could then use one of these data points and create a linear equation, no problem. Per usual, I like to start by sketching a quick graph of this situation. So I think that our independent variable is how many kilowatt hours you use, right? I think how much it even says it here, your energy bill, how much you pay for your energy bill, it depends on how much energy you use. So I'm going to put kilowatt hours down here, and I'm going to put your energy bill as our dependent variable. So let's see, when you used 315 kilowatt hours of energy, the cost to you was $90. When you used 360 kilowatt hours of energy, the cost to you was $99. Okay, so obviously we're suspecting that the more energy you use, the more it costs. And so we're gonna model this using a line. And I also like to make a table of values because I think a table of values is just a great way to organize our data. And on the left side of that table, we're going to have our independent quantity, our kilowatt hours, and on the right side, we're going to have our dependent quantity, our bill. So when we used 315 kilowatt hours, the cost was $90. When we used 360 kilowatt hours, the cost was $99. Okay, so we need to find out how much each kilowatt hour of energy cost. Well, how much did the bill go up between using 315 and 360 kilowatt hours? I think the bill went up $9. I mean, that's pretty obvious. You can just look at it. But I'm going to be really kind of thorough here. I'm going to call the bill our dependent variable, call it y, and I'm going to say the change in y. The change in our bill, well, was 99 minus 90, our final cost minus our original, and it was it's a positive $9 increase in the cost. But of course, that $9 wasn't for 1 kilowatt hour, it was for 45 kilowatt hours. So, and I just did that by eyeballing here. So if I told you that it cost $9 for 45 kilowatt hours, and I asked how much does it cost for 1 kilowatt hour, you would just divide 9 by 45. So 9 over 45, also known as 1/5, also known as 0.2. So I want us to be really comfortable using either decimals or using fractions as well. And of course, this 45 right here, that was the change in our x variable. Our change in kilowatt hours was 360 minus 315. So we used 45 more kilowatt hours in this other month. So a positive 45 change in the number of kilowatt hours you used resulted in a $9 increase in the bill, and this ratio will reduce to 5 kilowatt hours costs $1. So of course 1 kilowatt hour costs a fifth of a dollar, or 20 cents. And this is also going to show up in our graph. For 45 more kilowatt hours, the cost went up by $9, which of course means that if it were a 5-unit increase in kilowatt hours, the cost would go up by $1. Or heck, if it was a 1-unit increase in kilowatt hours, the cost would go up by 20 cents. This is not to scale. I mean, obviously it's not to scale. I'm freehanding everything, but I just want to show how this rate of change shows up in, of course, the table of values and also on the graph. And this is going to be the slope of this line that we are going to use to model this situation. And note to self, right, on our table of values, maybe I can create some space. Okay, there we go. Every time our kilowatt hour usage went up by 1, so if we use 316, it would go up to $90.20. Right, if it was 317 kilowatt hours, $90 and, thank you very much, 40 cents. And it would just go up by 20 cents every hour. Or, if it went all the way up by 5 kilowatt hours, so from 315 to say 320 kilowatt hours, the cost would go up by $1, so $91. And of course, if we count it one by one, 318, 319, 320, we'd have 90.6, 90.8, 91. So just all these different ratios representing the slope show up in our table of values and our graph. Well, here's the deal. Now we have all the information we need to create an equation to describe the situation. Because we know the slope of this line we're using to model the situation, we also know a data point on this line. And that data point is, and I know this is way off the graph, but I'm running out of space. We've got the ordered pair 315, comma, 90. So you can use the point slope form of a linear equation, or you can kind of use your intuition and say, listen, the cost, your bill, it quote unquote started at $90, it increased at a rate of 20 cents per kilowatt hour, or a fifth of a dollar per kilowatt hour. But of course, this starting cost of 90, that didn't happen when you didn't use any energy, when you used 0. It happened when you used, 315. So x minus 315. And maybe you guys are aware that I love this form of the equation. If you wanted to, you could have used the point slope form and started with y minus 90 equals 1/5 times the quantity of x minus 315. These are absolutely the exact same thing. You could have used the other point as well. The other point we've got on our graph is the point 360, comma 99. Awesome, and so we can use that as well, right? We could make our equation using the point slope form and write y minus 99 equals 1/5 times the quantity of x minus 360. Or as you know, I like more, y equals, so the cost, your bill would start at $99, kind of, and it increases at a rate of a fifth of a dollar per kilowatt hour. But of course, the quote-unquote starting cost, that wasn't when you use 0 kilowatt hours, it's when you use 360 kilowatt hours. So either of these would be fine. Now here's a big thing. If you remember before, we often used the year to represent one of our variables. So we'd usually have things like x minus 2007 or n minus 2009 or what have you. And for those equations, it really wasn't a good idea for us to put them into slope-intercept form. Because remember that the y-intercept happens when x is 0. And if x represents the year, we're talking about the year 0. I mean, we're talking about birth of Christ. And to be quite frank, I don't really care, what this mayor's approval rating was at the birth of Christ, or, some other things at the birth of Christ. But here, x represents how many kilowatt hours we use. And so it actually is important to us to kind of figure out, well, what happens when x is actually 0? So this is a situation when it would be a good idea to put this into slope-intercept form. Basically, my rule of thumb is if your variable equals the year, I don't really want to talk about the birth of Christ. That's probably not going to be helpful with regard to the modeling problem we're doing. But if x represents something like, how many gigabytes of data you used, or how many kilowatt hours you used, or something like that, it might make more sense. And if you put either of these into slope-intercept form, you will come up with the equation, I believe, y equals 27 plus 1/5 x. Let me make sure I actually got that right. 1/5 of 360 is 72. Awesome, yes. And so this means that if you use no kilowatt hours at all, your flat fee would be $27. So you pay $27 right up front before using any energy, and then each kilowatt hour costs a fifth of a dollar, or 20 cents. And so now that you've got this equation describing this relationship, if someone tells you how many kilowatt hours you used in a month, boom, you can tell them the bill. Or if someone tells you the bill, boom, you can substitute it in for y and figure out how many kilowatt hours you used. So a very, very powerful tool to be able to create these equations to describe these situations that we're going to model with a line.